Just let me know if I'm losing the connection, because I'm not 100% sure about the quality of internet here. So, yeah, my talk probably would be more theoretical, because today I'm presenting our review paper, which was recently published in Nature Reviews in Electrical Engineering. And the topic is neural architecture research for in-memory computing-based deep learning accelerators. And before I start my presentation, I really want to acknowledge all our authors. And without these amazing people, this work would definitely not be possible. So many thanks to them. This is a quick agenda for the talk. So I'll introduce what is software hardware co-design and why we want to do this. Then I'll move to hardware-aware neural architecture search methods and algorithms, and like hardware cost estimation methods, and conclude my talk with future directions and open challenges in this field. So probably you don't really need this introduction slide, just to briefly mention that as AI becomes more and more complex and the models become more and more complex, and in recent years, we actually see this exponential growth of the models. The power consumption that we need to, we actually need for training these models is very concerning, and the energy demand increase, and in turn, like carbon emissions also increase. So we definitely need more efficient hardware for AI applications. And of course, in-memory computing is, as already Dr. Van mentioned in his talk, is one of the solutions to reduce the data transmission between the conventional like processor and memory. But probably there is much more into this these days. I think we really should compare in-memory computing accelerators in AI context to other types of accelerators like GPUs and tensor processing units and so on. And in this context, we still have an advantage of having no data transmission between the memory and processor. So this roadmap was actually published, like I borrowed it from as a Nature Electronics paper, and it was published in 2020. And one of the open challenges there was like co-design of the good co-design toolchain for software and hardware. And this still remains a hot topic and open problem. We still don't have like a really good toolchain which we can just use to co-design device array architecture and like model parameters. So why do we actually need co-design? Is because if we want to achieve the optimum design in terms of hardware efficiency and performance accuracy, we need to optimize every level of in-memory computing accelerator, which means optimizing the devices, circuits inside, architectures and systems, and like models which we deploy into them. So very similar concept which have been already presented in previous talk. So this optimization is actually quite challenging, because there are so many parameters which should be considered, and like it's really impossible to perform all these co-optimizations manually if you want to come up with a certain preliminary design of the chip, which would be relatively good performing in terms of accuracy and in terms of hardware performance. And that's because there are so many parameters to optimize if you want to consider both search spaces of software and hardware. Like in one of the works which we like in our recent work, which we just submitted, we have a search space combining software and hardware parameters, and it can easily reach up to like 10 to 85 possible combinations, and that's definitely impossible to optimize all these parameters manually. So what we do, we also cannot use grid search approaches as the number of hyperparameters increase, like the search time like the number of search space, or like the size of the search space also grows exponentially, and we cannot have like a reasonable search in a reasonable time. So, and also on top of it, as the model complexities also increase, it takes much more time to simulate every model. So how to co-optimize it? Like, one of the possible approaches to consider is hardware-aware neural architecture search, which can be one of the possible solutions to obtain like preliminary design of in-memory computing hardware for the optimized neural network model. So what is neural architecture search? It comes from the initially from the software world, and from the software perspective, neural architecture search searches for the most optimal parameters in the neural network, such as we have like the search space of the number of layers, kernel sizes, different blocks, and so on. And the search algorithm can like we sample the different design configurations, and the search algorithm can help us to select the optimum designs based on the performance accuracy. Initially, this approach did not consider any hardware efficiency in the loop, or considered only like high-level measurement of like latency, for example, number of floating points per seconds. Then, if you want to move from that to the hardware concept, like if you want to extend the concept of NAS to hardware-aware neural architecture search, we might consider extend our search space and consider the hardware search space in the loop. So quite often it's either like we extend the search space to optimize the hardware parameters as well, or we just have the hardware feedback in this optimization loop. So what it actually does is similar to neural architecture search. The search algorithm searches for the most optimal neural network designs and sometimes hardware parameters, but the performance evaluation this time is done based only not only accuracy, but also different hardware metrics like just latency, energy, on-chip error, and so on. It depends on like what you are actually optimizing for. So in general, like in terms of like the bigger picture, there are like 4 different main like optimization parameters which can be considered in hardware-aware neural architecture search. One of them is model compression and pruning. So in this case, instead of like usual using just like pruning the neural network model, in this case we form the search, like form the quantization search problem, like quantization optimization problem as a search problem, and actually searching for the optimum precision, for example, in every layer, using like as a part of neural architecture search. Also, like hardware-aware neural architecture search can also search for different neural network blocks or entire architecture, or how they are connected. The search can be also more fine-grained in terms of like the size. We can search for the size of the kernel, search for like the size of the like number of channels, size of the layers, and so on. And we also can consider hardware search space in the optimization. So in our case, as we focus on in-memory computing, quite often the hardware optimization search space involves the sizes of the crossbar, number of ADCs per crossbar, how many columns are shared, and so on. And this is like just a general picture of what neural architecture search usually covers, which is like a neural network model, search space, and certain compression techniques. And to extend it to in-memory computing hardware, we can add the hardware search space in the loop. And yeah, it can be like very different hardware parameters, including like device precision, buffer sizes, resolution of the converters, and so on. Before moving to what are state-of-the-art frameworks for hardware-aware neural architecture search. I need to just briefly cover the main methods and which are used in hardware awareness. And these methods actually correlate with just the general concepts of the optimization, and these are pretty straightforward. So like the search method can be either single objective or multi-objective optimization. And single objective optimization can be divided into two-state methods, where we first search for the most accurate neural network. I mean, the neural network which would perform, which would have the best performance in terms of accuracy, and then optimize it for the hardware. And this approach is usually used when we want to deploy already well-performing model to a specific hardware. Constrained optimization would involve hardware feedback in the loop, and when we optimize the neural network parameters, we can always add like the feedback from the hardware, including like latency or energy. And that's this approach is useful when we already have the specific hardware platform and we want to optimize the model to fit into that. Multiple objective optimization involves colorization methods where we combine several objective functions together. So it can be accuracy and energy or latency. And that method can be quite useful because we can define the coefficient of this in this optimization and set up the priority of the functions. If we prioritize, for example, energy more than latency, we can run optimization based on this, and so on. And like Pareto-based optimization would give us the Pareto friend. So the trade-off between quite often it is between accuracy or hardware performance, or it also can be between like energy or latency, and energy or like latency or on-chip area, and so on. The other like important part of hardware neural architecture search is actually the search algorithm, which goes behind this whole like the neural architecture search framework. And in terms of state-of-the-art frameworks, these four are the most commonly used algorithms, which are like reinforcement learning, evolutionary algorithms, gradient-based methods, and some other methods like Bayesian optimizations also can perform quite well. I would say the most interesting one out of this is gradient-based methods, because quite often it is used in terms of constructing the big super network and sampling, like training it and sampling the neural network models from that. And this concept can also be extended into the hardware. So we can sample neural network models and specific hardware parameters, which is quite an interesting approach. And finally, the other like the last important concept in hardware neural architecture search is actually how we perform the cost estimation of our hardware. Of course, real-time measurements or the transistor level measurements are not possible in this kind of setup where we have so many neural network designs, like neural network models, and on top of the design parameters to optimize. So we definitely need some approach to perform it more like faster. Quite often, the state-of-the-art frameworks rely on lookup tables and analytical estimations, where we just record the like energy latency of certain like separate components. Or in analytical estimation case, it would be like mathematical formulation of like, for example, the energy consumption. These are not very accurate, but in the context of neural architecture search, where we just need like to assess the relative performance of the models. Like this can be quite useful and much faster. Like the last, I would say, most interesting methods of estimating the hardware cost is the prediction model. So the prediction machine learning or like new small neural network model is trained to predict how the hardware would perform. And based on our experience, it's not really accurate as well, but I mean, it would not be give you the 100% of like exact energy which you would achieve, but like it would give you like the relative performance, which is in terms of the search context is good enough. And why this is important is because all these cost estimation methods take time, and this contributes to the time of the search. And the faster the cost estimation method is, better it is for us. So we can assess the performance of more like large number of designs faster. Sorry. So this table is actually the table from the paper, but just redrawn in a better way to visualize it. So this covers all state-of-the-art frameworks available to our best knowledge for now for hardware neural architecture search for in memory computing context. And also we added some frameworks which appeared a little bit later after we published like our work. So like the main conclusion from this have several limitations in its frameworks. So we have, first of all, we have quite architecture search space in terms of every framework focuses on very particular neural network type. And that's why it's quite hard to actually compare the performance of these frameworks. Also, it has quite limited applications. Most of them just focus on vision tasks like object recognition, like image recognition. Also, most of them have quite limited hardware search spaces and include only very few parameters of hardware into the search, if they include them. Probably like the last two like have like a little bit bigger search space. But in general, like the main issue comes from the complexity of it. If you add hardware on top of the software, as I already mentioned, like you will have like very huge search space, and you would need to have certain techniques to sample the designs from the search space and evaluate them in a much better way, because you still want to keep your search time in like a relatively small. So you don't want to run your search for like several months. You still need like some reasonable time to complete it. So, and also there is like a lack of like unified framework which would consider different neural networks, and at the same time like different types of neural networks, and at the same time different types of in-memory computing hardware. Just to summarize, if you want to just have some bigger picture what hardware neural architecture search frameworks cover, so like in a broader perspective, they can be divided into like three main categories. Optimizing the model for the fixed constrained hardware, where we just perform the optimization of the neural network models. Optimizing the hardware for the fixed model, which actually is design space exploration. So this can be classified into like as a part of hardware neural architecture search frameworks, where we actually search for the best hardware parameters, and combining them, we would achieve like the co-optimization of software and hardware parameters, and like several state-of-the-art works are doing that. This is the roadmap for hardware neural architecture search for memory computing applications, which we came up with. recently, like the last 5 years, there have been some progress done in this area. Have been several frameworks published, but we still have a lot of interesting challenges to solve in this domain. Probably like I'll go through them very quickly one by one. And first of all is the complexity and the runtime issues in these kind of frameworks. We still have to evaluate a lot of models when we perform the search. So the amount of time we spend on the search is still increases if we extend the search space. So solving the complexity, like these runtime issues and search complexity issues is like a big deal for this kind of frameworks. Then we also, as an interesting thing, as a majority of the frameworks include the hardware non-idealities to them, but none of them actually include the mitigation techniques for hardware non-idealities. And that can actually help to improve the performance. So probably like consideration of the mitigation techniques in this kind of methods is actually important. Especially if this search is performed for like analog devices, like analog and memory computing, like rather than just SRAM based in memory computing. So also expanding the hardware and model search spaces is very important. So adding more applications is also very important. It's this concept can be applied to so many different problems rather than just applying it for the standard in-memory computing designs based on like vision tasks. This can be extended to like spiky neural networks, for example, for in-memory computing, like running on in-memory computing hardware, considering these parameters related to the spiky neural networks and or to the large language models if you want to deploy them to like probably a SRAM-based in-memory computing hardware and so on. So there is like a huge space to explore there. Further, like creating hardware wherein NAS benchmarks are important. So in software, NAS benchmarks it usually mean that we have like a huge lookup table with like all possible neural network configurations and related accuracies quite often. And why it is important to have this kind of benchmark as it allows us to ensure the reproducibility of the experiments and also allow us to compare different methods. So having something similar for the hardware part and for the memory computing part for neural architecture search would be quite useful. Then adapting the existing techniques of hardware neural architecture search methods for different memory computing hardware is also important. Quite often, because we have like limited number of tools available as a simulation tools. For example, quite often the simulation tools cover the certain very specific devices or very specific way to compute like inputs and outputs in for example in the crossbar array. This actually limits what the like designers and engineers do for hardware neural architecture search, because like it requires actually tools to simulate the hardware better. So what actually happens, majority of the frameworks are like designed for very specific in-memory computing hardware, quite often just covering ARRI-RAM-based solutions and don't go further. So that would be great to extend it. Further consideration of system-level challenges on top of this kind of optimization is also quite an interesting thing to consider. I'll cover it on the next slide, maybe more. And finally, like we don't have the unified framework, as I already mentioned, which would cover like different types of neural networks and different types of hardware, which is, I believe, would be a very great tool for to have as a especially to use this as a first step of this design. So just to mention quickly, in terms of what hardware-aware neural architecture search covers is quite often device search space. So for example, number of bits per cell, circuit level optimizations related to the crossbar, and neural network model optimizations. So sometimes some part of architecture related optimizations can also be covered, for example, like the tile size. But in general, like it doesn't consider any system level related optimizations, but architecture and system level actually related optimizations are the most important, as they can, like if this part of the hardware is not designed well, they can just kill the effect, or like the positive effects of in-memory computing. So what would be great to have is probably combining hardware-aware neural architecture search optimization techniques with certain optimization for system level and architecture level designs. So probably to have like end-to-end in-memory computing hardware optimization tool, which would cover the whole design space. And finally, just the final thought: if we would achieve the good, if we would solve all the previous challenges that I mentioned, we can go further and have fully automated neural architecture search methods capable of adapting and searching for the best neural networks and for the best hardware by themselves. So the equivalent in the software world would be like the AutoML0 concept, where the framework searches, like automatically searches for like complete machine learning algorithm, like including the operations and math and models. So there is like the main idea is that to have no human intervention in the design. So to like hardware awareness of this and also in memory computing awareness of this is like an quite interesting open challenge, but that's actually would take a lot of time to actually achieve the tools like that. But that has a huge potential to automate the design and to automate what the engineers actually do now manually. So yeah, this can, like, we can utilize AI capabilities to improve and automate both like algorithm and design. So, and basically that's my final thoughts, and I'm very open to questions. Let me just.
All right, thank you very much, Olga, for your nice presentation. Let me stop the recording.